What you're looking at is a spinning lenticular disc projecting 3D, so you get 3D parallax.
Fuck! That's amazing!
This is Will.
Hi, Will.
Nice to meet you.
A pleasure.
So the first stops were nanometer tools. Now we're going to do micron tools.
Okay.
So let's start over here. So if you look in here, you'll see dirt.
Yep, that
Dirt.
looks like dirt.
Dirt. And then if we look in here,
Oh, no way.
you'll see the dirt's micro Lego.
Yeah, but I can also see like...
Now, just for extra credit while you're there, here, let me get this set up.
Okay.
What you're looking at is actually a crazy tool.
Did it look a little 3D?
Well, no, it's actually, okay, here. Oh, good. Okay, so look in there and manipulate that. Just jiggle it around.
All right.
Like tilt it.
Oh, no way.
So you're getting micro parallax. What you're looking at is a spinning lenticular disc projecting 3D, so you get 3D parallax.
Fuck! That's amazing! Okay. I clearly can't afford one of these, but this is amazing.
You can't describe it.
Wow. You could do that for hours.
Right, and we do. So MIT made the first NC mill in 1952.
Right.
You can trace sort of all modern manufacturing to that, additive and subtractive. It's analog.
Right.
At that same time, Claude Shannon was digitizing communication and computation. The core research at heart that we're doing is, this is slightly bigger. That's like meso Lego.
Right.
If you compare Lego, which is like the proteins that Noah was doing, to a 3D printer, the geometry comes from the part, not the machine.
Right.
You can detect and correct errors so it's more accurate than the machine. You can join dissimilar parts, and you can unbuild as well as build.
So
it's digital.
Micro scale Lego.
It's digital. But it's digital in exactly the way Shannon and Van Neumann taught us. So what's going on over here is, you've used laser cutters before. So Will, if you start this up, okay, so that's making micro Lego, but if you look over there, you'll just see a blinking spot.
Right.
So this is a micro laser cutter. This is a laser cutter that makes micro scale things. And then what we're trying to do is assemble, if you take my phone, there's chips and packages on boards with traces, connectors in a case. We're trying to do all of that out of about 20 parts of micro Lego. Conducting, insulating, semiconducting, actuating, to build all, you're made out of 20 parts, the 20 amino acids.
Right.
We're trying to build all of technology out of 20 parts.
This will be the Lego, and this is clearly not the smallest size you're going to go for. This is...
So there's different sizes for different purposes. So this one, that's about a 20 micron curve. In the back, as we go by, I'll show you, we have an even crazier one of these, which is a laser. This is a diode pump solid state laser. We have a femtosecond laser, so the pulses are just a few cycles of light long. But the power is, during that pulse, is 600 megawatts. And that's enough to rip the material apart to make micron scale features. So those were nanometer scales. This is like 10 microns. In the back is this crazy femtosecond laser for 1 micron to make the micro to nano Lego. So
we have an array of parts.
So that's what Will just made.
That's what we were watching on video, this completely minuscule.
Yep.
And these, you're not cutting it out of this Kapton?
Yeah, exactly.
So amino acids, they don't have properties like transistor or motor.
Right.
They have properties like hydrophobic, hydrophilic. So in the same way, the micro Lego, one is insulating, one is conducting, one is magnetic. It's a level below things like logic or actuation.
Amazing.
So that's a micro insulating part.
Got it.
So that's Will.
Thank you.
Okay.
Can you can't even see this. Can you come in? You can't, I mean, Legos for gnats.
Okay, next stop, this way. So Will showed you micro Lego, and then he's making, in fact, you can see around the corner there, a beautiful assembler that's like a child playing with Lego, but it places the parts.
Got it.
And so the process is not printing or cutting, but assembling or disassembling.
Right. Right.
So, and that's, again, you're made out of a ribosome that assembles and disassembles amino acids. So the genome programs the ribosome.
Right.
Amanda programs the assembler.
Got it. Okay. Show me.
Yeah, so I'm working on a lot of design and simulation tools around these different processes that we're developing in the lab. So I was working on a tool that allows you to construct in this very modular fashion. So you can use parts, some parts are flexible, some are rigid, some are actuators, and you can construct these robots and mechanisms and things like that. And this is actually, we've been working with this gaming studio called Eline Media on turning this into a real video game.
And in fact, this is an immersive VR environment, but we're going to show you a different VR environment. We'll just show you this one on the screen.
Yeah.
Okay.
So this is kind of what this game looks like right now. So basically, I've constructed this robot here out of these different bricks.
And to explain, each of these bricks is a schematic representation of one of Will's bricks.
Right,
Like one is
right,
conducting, one is flexural, one is magnetic.
Right.
But they're made just schematically, so you can see what type of brick it is.
So I can kind of like use this paintbrush here to add different block types to this thing.
You can think of this as Minecraft with real physics.
Right.
And then when I put this thing in simulation mode, the cool thing about the game version of this tool is that you can actually map this all to keyboard shortcuts, and you can like actually drive these things through obstacle courses, which is a little bit different than the CAD tool that I'm developing.
Sure,
It's a little more
yeah.
serious.
But understand, that's not pretend. Next time you come, we should be able to actually show that working.
That it's a physics and full.
But also in reality.
Right,
Meaning
right,
this is
yeah.
to design.
I got you.
And the project this is leading up to, which is sort of the biggest project out of everything we're doing here, is to make an assembler that assembles assemblers
Right.
out of the parts that it's assembling.
So
And
it's-
it turns out you need that recursion to exponentially ring up assemblers. The heart of what Amanda's doing is to make the assembling assembler, you have to communicate a computation for a fabrication. You have to completely merge them. So you need to make a design tool that lets you communicate computation for fabrication. And that's what she's building.
Wow. That's really cool. Thank
Now, along the way to it, one of the processes you'll see, along with assembling and disassembling, we
Yeah.
do a lot of cutting and folding. So Amanda wrote another VR tool that we want to let you do in VR to interact with the structures. We're going to show you large-scale cutting and folding.
Okay.
And this is a design tool she wrote for that. So that'll be our next stop.
you. Okay.
Okay. So if you put this on,
All right.
then I'll help you tighten it. Yeah. And then, okay.
Yeah.
Then, let's see, these are on, so reach out
Fantastic.
and you can click and drag. Now with two hands, you can stretch it,
Oh wow.
you can muck with it, and then you can also throw it if you want.
It's kind of fun to shoot it like a rubber band.
You can, okay, grab one side, pull the other like an arrow, stretch it, and then if you let go, you can shoot it.
Ah. So I just did. There it
But she can
goes.
give you another one.
Another one here.
Or give you a different. So you're interacting with a physics simulation of an origami design tool.
Wow. Oh man.
And the colors represent the amount of stretching in the material, so you can see locally how much stretching is happening as you're manipulating it.
I see. I get you. Wow.
Give them the one with lots of little ones. That's fun to play with.
The little,
Yeah.
all right, shoot that one off to infinity somewhere. Okay, good.
Bye.
Here's another one.
Here. So here's a bunch of things you can play with. They don't yet interact. The other tool lets you snap them together.
But I can control the fold angle from outside, so I can like kind of drive them a little bit.
Wow.
Good. Any other shapes?
Let's do one more test.
Yeah, one more shape.
All right,
Alright.
shoot that one off. Hold on. Let's do. How about that one? This one's nice.
All right. Oh wow.
This is part of an emerging field of structural origami, where you can, in minutes, cut and fold things that would take hours to print.
This is from a single sheet.
Yeah, and we'll show you then the real things in a minute.
Fuck, that is so cool.
Wow. Let's see, Amanda, how old is this?
I've been working on this for a couple weeks.
Yeah, so this is a few week project and a few weeks old.
Yeah.
Wow. Okay. Good, thanks Amanda.
Great,
Next stop.
Thank you, Amanda. Nice to meet you.
So Adam, this is Ben.
Hi, Ben. Nice to meet you.
Nice to meet you.
So Will showed you the micro Lego.
Yeah.
But let's say you wanted to make a jumbo jet or a spaceship.
It's going to take a lot of that.
It's going to take a lot of that. We work with companies like Airbus or Boeing supply chain. The carbon fiber planes, the A350, 787, almost killed Airbus and Boeing. They were both like $30 billion investments. And to make them, the tooling's horrible. You need a tool the size of the airplane to wind the parts.
Right.
A tool the size of the airplane to cook it. They have these horrible tools the size of the airplane to put in the holes for the fasteners. Then you have these planes bigger than the plane to carry it. So a former student now at NASA, Kenny, showed that if you, here, Ben, hand me hand me that and then the other one.
Sure.
Kenny in his thesis showed if you take loops of carbon fiber and you link them, here, push down on that.
Whoa.
So wow.
Yeah.
So Kenny showed by making loops of carbon fiber, by an order of magnitude, it's the world's highest modulus ultralight material. So it behaves like a bulk material, much lighter than anything else, but it's completely reversibly constructed. So it's just like the Lego. The geometry is local, you can assemble and disassemble, but now it's to make aerostructures and space structures. But then it raises a question, which is how do you build them?
Right.
So Ben, how do you build them?
One way is GSWT,
What does that mean?
graduate student with tweezer. It works, but it's pretty slow. So this is an example of what we did with GSWT. This is using pultruded carbon fiber tubes, and we built a bridge structure, and then we took the parts apart and built it into a boat, and we took that apart and built it into a shelter, and all of it fit inside of these backpacks.
Amazing.
So this is really something that we were able to demonstrate to NASA, where you would have a really tight packing efficiency for a mission, be able to deploy it, and have multiple configurations and multiple different structures, all with the same kit of parts.
Okay.
Sure. But the real challenge is when you have hundreds or thousands or millions of these parts, what you need is robotic assembly.
Right.
So Will's assembler was bigger than the structures it's making.
Right.
So Ben's working on assemblers that are small compared to the structure they're making.
So this is Billy. This is Bipedal Isotropic Lattice Locomoting Explorer. He's designed, he's designed specifically to crawl around on the outside of the structure. So he just has these gripping end effectors and the minimum degrees of freedom to get around.
So what's
each
beautiful
one
about
is both a part assembler and a leg.
Yes.
Right. What's beautiful about Billy is he's free of almost all of the controls of a normal robot. All he has to do is like go ka-chunk, and each step re-registers him.
Right.
But show videos of how Billy moves.
Sure.
So it's beautiful the way Billy. So here, that's how Billy moves.
Oh,
So Billy does this very simple sort of inchworm motion. We've removed a lot of the complex metrology and sensing that a lot of other robots have, and basically it gets its precision from the structure that it's crawling
then those
on.
It's right. I
So
get
ready?
you.
These are Billy's kissing, and what they're doing is they're passing parts, and then this is an assembly head, so Billy can add and remove parts. And so the idea is an ensemble of little Billies can make a big thing.
And he needs just the most minimal instruction set to be
And
able to do that.
this can keep the ribosome makes the elephant because you can keep going.
Oh my gosh.
So along with Billy, we also have Mojo.
So this is the other adorable robot, which is once you build the structure. So if you show the video of this is a robot that goes inside the structure.
Right.
And so the robot can live in the structure, monitoring, repairing, doing operations in it.
Wow.
And so Ben and I did zero-G flights a couple months ago, testing this
In 0G.
to get it ready for, I don't know if you have those videos, but to get it ready for the space station.
Wow.
What he's showing right now is what we're working up to, which is to make things like kilometer scale.
Right,
So-
right.
Do you have us in the background?
I do. Give me
So
one second.
anyway, that's Billy locomoting in 0G. We're floating around it. I made the classic beginner mistake in 0G, which is I became a ballistic missile. That when it releases, I got up, and when you do that in 0G, you launch yourself and
Yes,
you become a
yeah.
missile, and then there's no way to stop, and you go flying into. Yeah.
So here is during one parabola. So we do about a series of 25 parabolas. It's 0 G's, 20 seconds at the top, and then
Yeah.
1.8 G at the bottom. So this is entering one parabola.
And
so
so
we
that's-
have this
that's-
test rig set up with suspended lattice structure and Mojo inside doing
And
his
then
thing.
part of the apparatus.
And then Neil
There you
is
go.
demonstrating the proper way to float in 0 G.
And this is getting ready to fly this on the space station to make a small thing that can make big things. So you can
Right,
flat
right,
pack space
right.
structures.
That's beautiful.